Hi everybody, and welcome to our final lecture for Math 1000. In this lecture, we're going to cover two sections, sections 3.4 and 3.5 in your text, and we're going to talk about rational, radical, and absolute value equations, and also absolute value inequalities. Let's start with rational equations. So first of all, with the word rational, you see the word ratio in it, and a fraction is a type of ratio. So with rational equations, you see fractions here. Now they can be simpler examples with just regular fractions, or typically, and in most cases, they're more complicated than that, and they have a lot of variables oftentimes in the denominator. So we'll look at both cases here. A great way to work with these is to actually solve them by canceling the fractions. And to do this, so to clear out the fractions, we multiply both sides of the equation by some sort of common denominator. And we do recommend the least common denominator since obviously smaller numbers make your life a little bit easier in the long run. A really important thing though is that we do have to check our solutions to verify they work. It is possible to get extraneous solutions when solving both rational and later radical equations. Extraneous solutions are basically answers that don't actually work. So when you're solving the problem, everything seems fine and you may get a nice answer or more than one answer sometimes. But when you go to check that solution back into the original equation, it just doesn't work. So you do have to check your answers to rational and radical equations because it's not always obvious when you have these extraneous solutions. The reason they occur is basically when we start multiplying by variables on both sides of the equation, it can create extra solutions. So that really is the problem here. It doesn't usually occur if your denominators are just numbers, so we'll still check our answer here, but that's not typically the issue. The issues tend to come up when you have more variables in your denominator because we're going to have to multiply by variables, and that process sometimes creates extra solutions by accident. All right, so let's look at our first example here. And I'm just going to rewrite this because it's a little bit hard to read and see. It's a little small. So for our first thing we want to do is I'd really like to clear out the fractions. If there are parentheses first, or anything easy that you can do to simplify, I do still recommend that. So if I had parentheses and I could use distributive property, I would probably still do that first. But otherwise, except for those kind of very basic simplifying techniques, I want to cancel those fractions pretty early on in my solving process. And I'm going to do that with the LCD. So here, I want to note my two denominators are 3 and 2. So I'm going to try to find a common denominator for both 3 and 2. And we can use 6 here. A common denominator should be one that both of these can multiply to very easily, right? 3 times 2 is 6, 2 times 3 is 6. So they're factors of the LCD. And then what I'm going to do is I'm going to multiply both sides by that 6. When I do that, I am going to distribute through. So you end up with 6 times x minus 8 over 3. And then 6 times x minus 3 over 2. And we still do the other side as well. Even though there's no fraction there, we have to keep everything balanced. So that's why both sides get multiplied equally. And then what we're going to do next is we're going to divide first. So 6 divided by 3 is 2 here, and 6 divided by 2 is 3. And if you found the correct LCD, your whole fractions should be canceled out at this point. And we're just going to keep simplifying. So I'm going to multiply that 2 and that 3 through on the numerators here. So here I'd have 2x minus 16 plus 3x minus 9. And then on the other side, 6 times 0 is 0. You do want to be careful. I do have a plus sign in between, so I'm distributing a positive 3. If there was a minus sign here, though, be careful. You'd want to distribute that negative as well. So that's an easy mistake to miss. At this point, it should be more straightforward. So 2 plus 3 is 5, so this is 5x. Minus 16 and minus 9 gives me negative or minus 25. Oops. And then I'm going to keep solving. I add 25 to both sides, divide by 5. So the goal is to kind of do the fraction work up front so that the hard stuff goes first, and then hopefully you're left with a simpler equation afterwards. Again, you want to get in the habit of checking your answer here, and you always check it back in the original problem, which is really important. If you check it halfway through, it's not a full check. So you need to go back to the beginning, and you want to check by just plugging in, not by like solving or anything like that. You just want to take that 5, plug it in, and see if it works out. So here I have negative 3 over 3. Here I have 2 over 2, and we get negative 1 plus 1 equals 0, which is true. So this does check out, and x equals 5 is a true solution. All right, let's do the next one. Now for this one here, I have basically only one unique denominator, and that is x minus 3. Now, when you have plus or minus like this with the variables, you do want to make sure everything is completely factored. They are here, so these are factored. There's nothing else I can do. And then these factors stay together. They're a single group. It's not an x and a negative 3 separate. It's x minus 3 as the factor. Because I only have one unique factor here, my LCD can just be the x minus 3. I don't need to use a square here. I only have one in each case, so 1 is fine. And then I'm going to go ahead and I'm going to multiply both sides by x minus 3. Now for this one's actually pretty quick because this x minus 3 will cancel with this one, and this x minus 3 will cancel with this one. So we're left with just x squared equals 9. We can solve this by taking the square root of both sides. Don't forget the plus or minus. So I have x is equal to plus or minus the square root of 9, and the square root of 9 is 3. So I have two solutions here. One is x equals 3, equals 3, and the other is x equals negative 3. Now don't forget, before you're done, you do want to go ahead and do those checks. So I'm going to start with x equals 3, and again, I'm going right back to the original to plug it in. So be careful here. I'm going to get 3 squared over 3 minus 3 equals 9 over 3 minus 3. And I end up with 9 over 0 equals 9 over 0. Now, they are the same, but we have a problem here. We're dividing by 0, and we cannot have that, right? That is undefined. So this cannot be a solution then. So here I was checking positive 3. Even though they're the same, it doesn't work. I can't have any domain issues here. So x equals 3 gets thrown away. And also a lot of times you can find these domain issues right away. So in this case here, I don't have any x's in the denominator, so there's never going to be a chance for our denominator to be 0. So our domain there was all real numbers. Here though, we need to make sure our denominator is not 0. So when you solve this, you do see right away that your x value cannot be 3. So that one can get thrown away. You still want to check the other one though. Just because one gets canceled and one does not mean the other one always works. Both of them may not work for different reasons. So it's not just domain issues that you're watching out for. Sometimes they're subtle and you may not notice them right away. So you do have to check. Here I get negative 3 squared, negative 3 minus 3, 9 over, oh sorry, this is a 3 here, 9 over negative 3 minus 3. Negative 3 squared is positive 9. Negative 3 minus 3 is negative 6. So I do get the same thing in both cases, and there's nothing undefined here. So this one is perfectly fine. So our only solution here is negative 3. This one is a perfect example of an extraneous solution. And again, they can occur because of domain issues, or they can just occur. So sometimes it will be fine with the domain, but when you plug it in, it still doesn't work. So again, you want to get in the habit of always checking and being really thorough with your checks here. All right, so our last example here for this style is this one. And this one's definitely a little bit harder, right? So we're kicking it up a little bit here. And you do want to make sure you start, if you need to, by factoring the denominator. So here, this is much more complicated. In our first two examples, the denominators were pretty simple. Here, though, I see squares, I see common factors. So I want to start by factoring my denominator if they're not already done so. So I'm going to take out the 3 here. And then this actually factors as x plus 2, x minus 2. And the last one I can't do anything with. So I do see I have three different kind of denominators here. So let me look at all my factors. In the first case, my denominator is, so 3 and x plus 2. In the second case, my denominator is x plus 2, x minus 2. And then in the third case, my denominator is x minus 2. So to find your LCD, you want to make sure you have all possible factors there. So what I like to do is just go through one at a time. So I typically will take the entire first group because you need all possible factors. So I need that 3 and I need the x plus 2. And then I'll look and see, well, what else do I still need? So if I go to, so these guys are done. If I go to the next group, I need an x plus 2 and an x minus 2. Well, I already have an x plus 2, right? That guy is already there. So I don't need it again, but I do need an x minus 2. All right, so that one's taken care of. Then I go to my third group. I need an x minus 2, but again, I already have one. So I don't need to add it in again. And my LCD that I'm going to use is this right here. As a side note, the only time I would add in another of the same factor is if one of these was a square. So for instance, if this was, an x plus 2 squared, then I would need to incorporate the square there and have 2 of those factors. That's not the case here though, so 1 is sufficient. Now I'm going to go ahead and take my LCD and multiply it by all parts. I'm going to go ahead and do that on the back so I have some room. All right, so there's my LCD, and I'm going to multiply that by 2 over 3 times x plus 2 plus 1 over x plus 2 x minus 2. And then on the other side, again, I'm taking my LCD, and I'm multiplying it this time by 4 over x minus 2. Sometimes the worst part with these is writing them all out. There's quite a lot of steps here. I do need to distribute this through. So a lot of times you can kind of skip the first step for writing if you know you're going to end up distributing and just kind of jump to the next piece. So the LCD gets multiplied by 2 over 3x plus 2. And then it gets multiplied by 1 over x plus 2, x minus 2. And then the right side just stays the same for now. And I'm going to start canceling. So notice on the left here, I have a 3 in common and an x plus 2. So I only have this part left. Moving over, the x plus 2 and the x minus 2 cancel. So I have a 3 being multiplied by a 1. And then the last piece, I just have an x minus 2 that cancels. So I have this and this left over. And we're going to multiply what's left. So you may have to do a little bit of distributing here, right? That 2 is going to come on through. And I'm going to get 2x minus 4. For the next group, it's a plus, so positive 3 times 1 is positive 3. On the other side, we want to be a little careful here. I have a couple steps. So I see a 3 and a 4. So 3 times 4 is 12, and then you still have this x plus 2 left over. So I do have to distribute. So when we multiply, just do 2 things at a time. And I have 12x plus 24. Now I'm going to go ahead and keep solving. So on the left, I'm going to combine my like terms there. I'm going to go ahead and subtract the 2x from both sides. I'm going to subtract the 24. And I'm going to divide by 10. And finally, I get that x is equal to, these can both be divided by 5 to simplify that fraction. So I have negative 5 over 2. Now, negative 5 over 2 is perfectly fine here. You could change this to the decimal in this case if you wanted to, because it does come out even. It comes out as negative 2.5, depending on which format you want your final answer in. Now, unfortunately, you are not done. You do have to do a check here. So you would want to go back to the original problem, which is 2 over x, 3x plus 6 plus 1 over x squared minus 4 equals 4 over x minus 2. And you do want to go through and check this. Now, you can check it in the fraction form, or you can check it in the decimal form. You just want to keep in mind if you're using decimals, you may have some slight rounding error. Here it should be okay, but it doesn't always work out that way. So you just want to be a little careful if you are checking with decimals. You could be a little off in here, but it should be very, very close, if not exact. So here, let's go ahead and we'll just do a check with fractions. I think it's probably a good review for everybody anyway. Mom, can I cloud? And I'm going to go ahead and plug that in and keep going. Now, I did do a lot of this out ahead of time, so I am going to speed it through a little bit so we're not doing too much time here. So here you do have negative 15, right? There would be a 1 underneath. So it's negative 15 halves plus. Now, 6 is 6 over 1. You are going to need common denominators here, so I'm going to change that over to 12 halves right away, multiplying those both, by 2. When you're squaring, you can distribute that through. So you're going to have positive 25 over 4. And again, that would really be 4 over 1. So if I want to have common denominators, I'm going to multiply this by 4 over 4. So minus 16 over 4. And then here again, that would be a 2 over 1. So getting a common denominator of 2, it would be 4 over 2. This becomes 2 over negative 3 over 2. Plus 1 over 9 over 4. And then on the right side, we have 4 over negative 9 over 2. Now, these complex fractions you can deal with in many different ways. One way is to note that this really is a division bar. So what you're doing here is you're basically just dividing by that denominator. And with fractions, that means flipping that second fraction and changing to multiplication. And that's going to happen in all the cases here. So when you do that in each case, for the first one, you're going to get negative 4/3. In the second case, you're going to get 4/9. And then in the last case here, you end up with negative 8/9. And again, I'll let you do some of that at home. We're just about done. I do need common denominators here, so I can multiply this by 3. And I have negative 12 over 9 plus 4 over 9 equals negative 8 over 9, which is finally true. Negative 12 plus 4 is negative 8, and I can finally say that this actually does check out. So some of the checks can be pretty tedious. Again, you could use the decimal here as well on your calculator. Just note and just be careful with rounding errors and things like that. So sometimes the decimals do get a little bit weird with some rounding errors. But again, your checks should be very, very close if you are using a decimal. All right, so for rationals, things to think about. Wanting to use the least common denominator to multiply through to cancel out those fractions, watching out for extraneous solutions, making sure to check our answers as well, and then also watching out for domains. So do remember that, we still have domain restrictions here. So if I'm looking at my domain, I do need to make sure my denominator is not 0. So for instance, we need to make sure that 3x plus 6 is not 0. X squared minus 4 is not 0, and x minus 2 is not 0. So you have quite a lot of restrictions in this case. So in the first case, x cannot be negative 2. In the second case, when you solve and take the square root, don't forget it's plus or minus, so x cannot be positive and negative 2, And here we also get 2 again. So the two big issues here are positive 2 and negative 2. And luckily, neither of those came up for our solving process when we solved and got negative 5/2. So there wasn't no domain restriction here, and then it also checked out. And again, just keep in mind that extraneous solutions can happen just from the check as well. They don't have to be domain issues. So that's something to watch out for. As I know this week in the discussion, we're looking at checks there for our radicals as well. All right, the next type of equation I want to talk about are radical equations. So these are ones that have roots in them or radical signs. And again, these ones we do have to check as well. So don't forget to check. Oops. For extraneous solutions here too, so they can occur here as well. Now to solve for these, we do it actually a little bit differently. You do need to make sure to isolate the radical first. So if the radical is not by itself, you'd want to get it alone. Here it's already by itself, so we can jump right in. And then what you're going to do is you're going to use a power to cancel. So remember that roots and powers or roots and exponents are opposites. So if I have a square root, I'm going to use a power of 2. If I had a cubed root, I would use a power of 3. If I had a fourth root, I'd use a power of 4. So you use whatever that same index is to help cancel. So here I have a square root. So I'm going to use a square, and I'm going to square both sides. And what happens is that square root and that square cancel. So you're left with 3x plus 1 here. And in this case, 4 squared is 16. We subtract 1 from both sides, divide by 3, and we have our first solution of x equals 5. Now again, you do have to check. So I know it's a lot of extra work sometimes, but it really is something that you have to do for these, not just to make sure you got the answer right, but again, because extraneous solutions do come up quite a bit. So you do want to make sure that you're getting a nice true check here and that it really is a solution. As I noted too, again, if you see something with a cubed root, like let's say I had the cubed root of, I don't know, 2x plus 1 equals, let's see, we'll do 3 here, for instance. Then what we're going to do, if you have a cubed root, you would cube both sides. Again, your root is isolated, so it's going to cancel right out. 3 cubed is going to be 27. And then I would keep solving from there. And you still have to check it, okay? So if I go ahead and I check this, I'm saying, okay, is the cubed root of 2 times 13 plus 1 equal to 3? Well, 2 times 13 is 26 plus 1 is 27. And yes, in this case, it does work out. So whatever your type of root is, that's the power you're going to use to cancel. Now, our second one here is a little bit more complicated. I just have a square root, but it's not isolated yet. So I do want to get the root by itself. I'm going to bring this 5 to the other side. If it's positive here, it becomes subtraction or negative over there. And now I am finally isolated. This is a square root, so I'm going to square both sides. And just be careful, this one's a little bit harder because when we square the other side, you have to FOIL this out. This doesn't just become x squared and 5 squared. It has to get multiplied out and FOILed. So you get x times x is x squared minus 5x minus 5x and then plus 25. Cleaning this up a little bit, the right side becomes x squared minus 10x plus 25. And then now think about this. I have a square, so I want to think about, well, how would I solve a quadratic, right? The rest of them have been linear. This one's quadratic. So we can try factoring. We can try our quadratic formula, completing the square, etc. So you're going to use one of your strategies that work there. I'm going to bring everything to the right here, just so I can clean it up and get my like terms together. So these are both going to come over. I'm going to do it in one shot. So I get 0 equals x squared minus 11x. This is going to be plus 18. Now this one is actually factorable, so I'm going to choose to use the factoring technique here, but you could also use quadratic formula here as well. That one works really nicely. And then don't forget, for factoring technique, when you're equal to 0, you set each factor equal to 0 and solve. So my first solution is 2, and my second solution is 9. Now don't forget, we do have to check these, right? So we're not quite done. And when you check, you have to go back to the original. So be really careful there. A lot of times students check it halfway through. You want to go back to the original. Let's see, let's check x equals 2 first. And I'm going to plug it in. So here I have two x's, so they both going to get 2. 2 plus 7 is 9. So this becomes 5 plus 3 equals 2. And this, of course, is not true, right? That would be 8 equals 2. So 2 is actually not a true solution here. When you check again, you want to just check by plugging in and simplifying. Again, a lot of students try to square things and make it more complicated, but you want to do the most basic check you can. That really is the way to check that it works. I'm going to do the same thing here. So I go back to the original. And just because one of them fails does not mean the other one automatically works. There have been cases that they both end up not working, so you really have to check them one at a time. Here that doesn't happen, so x equals 9 is a true solution. Now for my last example here, again, we're kind of taking up another level. So we have the square root of x minus 3 plus the square root of x plus 5 equals 4. The way you start is you have to isolate your radical. So what do you do when there's two radicals, right? So when there's two radicals, you actually want to bring one of them to the other side. So it doesn't matter which one. I want to bring this one over. And if it's a plus here, it's going to be subtracted. So when I bring it over, it's going to look like this: 4 minus root x plus 5. And now I'm going to try the same technique, but it is going to be a little bit more complicated. So I have a square root, so I'm going to square both sides. And this one that's totally by itself will cancel. So you're going to be left with x minus 3 on the left. The one on the right is much harder, though, because I can't just cancel this one piece. It's a whole group here, so the whole thing has to get squared, meaning that the whole thing has to get FOILed out. Right? It's not just 4 squared and then x plus 5. That's not how it works. We have to actually multiply the whole thing out here. So I get 4 times 4, which is 16. And I have 4 times that negative root. Now, when you're multiplying a number by a root, right, and there's no root here, what happens is that 4 just stays on the outside. And the same thing on this piece here. That 4 is just going to stay on the outside there. You're not actually going to multiply it through. Here, I have a negative and a negative, so that would become positive. And then I have a square root of 5 plus, or sorry, times the square root of 5. So you're squaring that piece. So what happens is you have a 16. Now these guys are like roots, right? They're the same kind of root. So if they're the same kind of root, they kind of just work like variables, and we can add or subtract like roots. So I add or subtract the numbers on the outside. Negative 4 plus negative 4 is negative 8. And then I leave the root alone. Here, this square root and square will cancel, and I'm left with just x plus 5. Now I'm running out of room here, so I am going to move on the back at this point. So let's rewrite what we have so far. Okay, and then I'm going to keep going. So on the right side, I do notice I have a 16 and a 5, so I can combine those into 21. I have an x just kind of left over and hanging around, and then I have minus 8 root x plus 5. I see some like terms on the other side, so I'd like to get them together. I'm going to bring the 21 over. So I have x minus 24 is equal to x minus 8 root x plus 5. And I'd also like to bring the x over as well. Now, in this case, when I subtract the x, it ends up canceling on both sides, right? Because x minus x is 0. That doesn't always happen, but it does here. So I'm left with this. And I'm going to repeat the process now. So I still have a root left over, which I need to cancel. So I need to get that root by itself. And again, if you have more than one root, you may have to do this process more than once and start isolating that root again. So I'm going to divide both sides by -8 just to clean it up a little bit more. And that leaves me with 3 equals the square root of x plus 5. Now I'm going to repeat that process. To cancel a square root, I'm going to square both sides. I have 9 equals x plus 5. And finally, I have my answer of x equals 4. I'm not quite done though. You do have to go ahead and check. So I go back to the original problem to check. So that was square root of x minus 3 plus square root of x plus 5 equals 4. I plug in that 4. I get 4 minus 3, 4 plus 5. Now 4 minus 3 is 1. 4 plus 5 is 9. Square root of 1 is 1, square root of 9 is 3, and this happens to work out as well. So this is a true solution. If you get an example where, let's say your checks don't work for any answers, you could have no solutions, and that does happen. So you do want to expect to watch out for no solutions here or there as well, but obviously not every single problem. All right, the last we're going to look at are absolute values. Now, these are a little bit nicer because we don't have extraneous solutions in these cases. It is good to still check your answers to make sure you solved it correctly, but you're not going to be worrying about extraneous solutions here unless you were combining an absolute value with a rational or with a radical, then that's different. But if it's just a kind of straightforward absolute value, a pretty basic one, a regular check is fine, just to make sure you're on track. So the first thing I want to note is absolute value is just the distance to 0. That's all it is. So for instance, when I say find the absolute value of 5, you're literally asking yourself on a number line, 1, 2, 3, 4, 5, how many spots away is 5 from 0? And of course, it's 5 spots. If I ask you for the absolute value of -5, 1, 2, 3, 4, 5, again, you're saying, well, how many spots am I from 0? But it's still 5. So what happens is absolute value is going to be positive. The only time it's not positive is if you're taking the absolute value of 0, which is just 0. Otherwise, you're going to have a positive answer because distance is positive. So notice here how two different values have the same absolute value. And again, the only exception is 0. So when you're solving something, what we're going to do is, first of all, you do want to isolate the absolute value. And that is really important. And when you isolate the absolute value, the other thing that's key is that the number on the other side should not be negative, right? Because the answer to the absolute value problem is always going to be either positive or potentially 0. But it's not ever going to be negative. So this is a good check. If that happens, then you would have no solution in that case. Once it's isolated, then what you do is you basically split into two problems. So you take whatever is inside the absolute value, and you set it equal to the right side, and then you do it again, but set it equal to the negative of the right side. And then you solve your equations that way. So let me show you another example that actually involves a little bit of work so you can see how it turns out. All right, so for here, notice that my absolute value is not isolated. So I do want to bring that 1 over first. And this is actually a really important step. If you don't isolate your absolute value, one of your answers will end up being wrong. I'm sure there's always an exception here or there, but in general, if you forget that first step here, when you split, it doesn't work out the right way. So you want to isolate the absolute value first. Notice how once my absolute value is isolated, make sure your right-hand side is a positive, and it is. So that is a nice check. If it's not a positive after you isolate, then you can't go any further. It's a no solution. Now we're going to go ahead and check. Sorry, not check. We're going to solve. So I'm going to split this 1 with 5 and 1 with -5. So this part doesn't change, just the right side changes. And then I can go ahead and solve. So here I have 8. And here I have -2. Now I am going to show you the check again, just to show you why it works. So if I go back to the original and I check 8 first, I have absolute value of 8 minus 3. 8 minus 3 is 5. And the absolute value of 5 is 5. So you end up getting 5 minus 1 equals 4, which is true. When you check -2, you would have absolute value of -2 minus 3 minus 1 equals 4. -2 minus 3 is -5. And then the absolute value goes back to positive. So you get another solution. So that's what's happening here. That's why you set it equal to positive and negative, because you're getting those two chances to get that outcome. Again, the only time you don't have a positive or negative is if your absolute value is equal to 0, because 0 can't be positive or negative. But otherwise, you should always have two answers. And as a note here, again, if that absolute value is less than 0, it's not a solution. So your absolute value cannot equal a negative. You do want to be really careful here. So you don't want to make the call too early. So for instance, if I look at an example like this, it seems perfectly fine. Everything is positive, right? I don't have any negatives. But my absolute value is not isolated. You have to do that first. So when I isolate that absolute value, I now see that I get the absolute value is equal to a negative. This is a no solution. All right, so watch out for these. And it works the other way too. So for instance, you could have something like the absolute value of 3x minus 10 equals -5. And you think, oh, I have a problem here, but you're not ready yet. You have to isolate the absolute value first. And when you do, you actually see that it's equal to +5. So it's fine. There's nothing wrong here, and you can keep going. So again, make that call after the absolute value is isolated. All right, the last piece I want to talk about here are absolute value inequalities, meaning less thans or greater thans. It's still going to be the same idea where your A value should be positive, okay? But we have two styles here. So one is when you have a less than, and this could be less than or equal to, works the same way. And the other is when you have a greater than or equal to. So there's two styles that you could have here. So let's look at them. And again, notice how the absolute value is isolated first. So if it was not isolated, you want to do that and get it cleaned up before you start. So here we have absolute value is less than +5, so everything seems fine. And I have a less than sign, so I'm going to follow this format here. So what you do is you take that 3x plus 2, you leave it as less than 5, and then you're going to make a sandwich on the other side with greater than here, -5. So notice you're still getting kind of two cases, right? The 5 and the -5, but we're writing it as an inequality. So when it's a less than sign, it becomes a little sandwich. And then what you can do is just solve these how we normally have. Subtract the 2 on all sides. And divide by 3. And we have our solution set here. So we're going from -7/3 is less than x is less than 1. This is fine. If you don't like the 7/3, you could change it to a mixed number. For instance, it's -2 1/3. That may make it a little bit easier to kind of understand. You could write this as interval notation. These are both less than signs, so I'm going to use parentheses. And of course, you could also graph this. And you're just going to do your best to estimate. So 1 is pretty clear, right? But -2 1/3 is probably maybe like right here. And because I have those less than signs, I'm going to go ahead and use parentheses. This would be like using open circles, right? If you've seen it that way before. All right, our last example here is very similar. So your absolute value is isolated. Again, the other value is positive, but here you have that greater than sign. So when you have a greater than sign, we set up a little bit differently. This is an and style problem when you have that little sandwich. When this one is an or style. So again, you rewrite that 5 minus 2x and you keep one side the same, greater than or equal to 1. So kind of one side doesn't change. And then the other side becomes 5 minus 2x is instead less than or equal to -1. So the 1 becomes a negative, and that sign flips as well there. So again, it's a little bit different. We cannot write this as all one piece because of the way the signs work. And now I'm going to solve. So I subtract 5, divide by -2. Don't forget when you divide by negative, you have to flip that inequality sign. So it's going to become less than or equal to +2. Over here, again, I'm going to divide by a negative, so I'm going to have to flip that sign. And I have x is greater than or equal to 3. So if I look at a graph here, let's see, 0, 1, 2, 3, 4, 5. So for this piece here, x is greater than or equal to 3. We're starting at 3. We're going greater than. Oops, sorry, I forgot to color in the middle piece there. I guess that would be better. And because I have an equal piece, it's going to be a bracket. And then I have x is less than or equal to 2. So here's 2. I want less than. And again, we have that equal piece, so we're going to have a bracket. This would be the same as having closed circles. Again, if you've seen this before, usually in high school, they tend to teach it with the open and closed circles instead. This is correct. So x is greater than or equal to 3, or x is less than or equal to 2. So that is a correct way to state it. Or using interval notation is a little bit nicer. You just want to go in order. So -2 is smaller, right? So it's going to go from -infinity to +2, excuse me. And then over here, we're going from +3 to +infinity. And then again, we just put that u in the middle to represent that the two parts are being united or combined together for the final answer. So this last section here that we're covering is sort of a little bit of a mishmash of other equations that we haven't quite touched on yet, right? So they're ones that maybe don't get used as frequently as some of the other ones we've seen, like linear and quadratic, but they still do come up. So you do want to know how to deal with those fraction equations, the radicals, and also the absolute values. Again, if you have any questions, please send me a message. I hope you guys have enjoyed the class and that you're doing well finishing up our last week. So just keep in mind our deadlines this week are fixed, so there's no late homework or anything like that because the term is ending. So just make sure all your work is in on time because I cannot accept anything late. And of course, if you have any questions, send me a message.